Our next speaker will be Dr. Laxmikant Kale, who is professor at the University of Illinois in Urbana-Champaign. Dr. Kale is the director of the Parallel Programming Laboratory and research professor. And in 2016, he received the Paul and Cynthia Saylor Professorship in Computer Science. He is the fellow of the ACM and IEEE, from which he received the Sidney Fernbach Award in 2012. Dr. Kale has been working on various aspects of parallel programming. His collaborations include the widely used and Gordon Bell Award-winning nanoscale molecular dynamics program, but he might be best known for the parallel object-oriented framework CHARM, CHARM++, which was also the basis for him and his team to win the HPC Challenge Award at Supercomputing in 2011. And in today's talk, Dr. Kale will show us how to deal with the end of Moore's law with parallel computers. Finally, over to you.
All right, thank you very much. Let me see if I can get my, one thing I must say, you forgot in your introduction that you wouldn't have, not your fault, is that you said you are this and you are that. And I think the last point is I'm barely awake. I'm calling from the US. I'm not used to waking up early. So hopefully my coffee will keep me alert enough. Let's see, share screen here. Yeah. Is my audio okay?
Your audio is okay, and we can see your screen.
Okay. Excellent. So I'm going to talk about parallel computers finally, and I will explain the title a little bit. I'm going to do a little bit of a subjective personal take on this. So first, I want to say, why do you want faster computers, faster and faster computers? And I will take a little detour with history of computers and through Moore's law, and why this virtuous cycle is ending, and where do we go from there? And that's where we will get to parallelism, and then talk a bit about distributed computing and supercomputers, which is where a lot of our work has been, and then talk a small bit about how to program these supercomputers, in particular our methodology for doing that. So, so to tell you why I need faster computers, I have to take a small detour. Maybe 120 years old, around 1900, scientists had basically started predicting end of science, right? Say, okay, we're done with science. We know all the phenomena. Well, there's this little niggling Lorentz something or the other, but then most everything is known. And then it turned out, came Einstein and appended all of that. And then we started with this new relativity thing. And soon in quick succession came quantum mechanics with all kinds of results. And then at the end of that, maybe 30-year period, that was a very heady time. And this time it really did feel like we got everything. Maybe just a little bit of quantum gravity stuff, but that can come unification of all forces. It didn't seem to impact any physical phenomena and predictions for physical phenomena. So some people started saying, in fact, I'm not sure there is actually someone who said it. I will tell you who said something more close to it, that laws of nature are now completely known and all that remains is mere calculation. Not quite the same thing, but Paul Dirac actually said the fundamental laws necessary for mathematical treatment of physics and chemistry are known, and didn't say mere calculation. He said the real problem is that these equations are too complex to be solved. Right. In other words, he understood the complexity of what needs to be done. And so the 20th century was full of efforts to make quantified predictions possible using approximations, using all kinds of math and so on. And then this is where the computational science begins. Why do we want this? Well, powerful computers can be used to predict physical phenomena. And then with that, you can do great positive societal impact with things like novel materials, with biomedicine, molecular medicine, engineering design, and so on and so forth, and not to leave out understanding the universe as a species. That's like that. We are a civilization we have a right to understand the universe, may not have a societal benefit. We are just curious species. So, so variety of things like that become possible only because of faster and faster computers, and we still don't have enough power to do all that we want to be able to do. So if you look at weather simulation, I'm not sure I'm going to, well, okay, weather simulation is one of those examples where you need to discretize space, deal with the moisture and some variability and so on. And these simulations take a long time, and weather is a chaotic phenomena. If you have the so-called butterfly effect, where a butterfly flutters its wing in Beijing, and there is a thunderstorm in Oklahoma 10 days later, right? And there was small changes in initial conditions can have big impact down the line. And so numerical simulation is necessary to just predict a few days or maybe 1 or 2 weeks into future if we do accurate simulation and all kinds of ensembles. So so that's one example to start with. But then let's talk about so we know that computational science requires these big fast computers. Now let's take a little bit of detour on how do you make computers faster. So computers are built from, again, I'm going to belabor you through this little detour. Apologies to people who know much too well this material, but computers are made from very simple components, switches, a controllable switch, which is turned on and off by electricity. And with that, you can build AND gates, we can build OR gates. With those AND and OR gates, you can build adders, and with a little feedback loop among those gates and switches, you can make memory. And with memory and combinatorial circuits, we can make, with lots and lots of those components, we can make a whole computer with registers and ALUs and so on and so forth. It's all nothing but switches sitting on semiconductor. Now, there is some specialized memories that are simpler than switches, but let's leave that aside. And let's keep on talk about this very simple computer. Keep that in mind for a second. Now, if the computers are made from these simple switches and we get complexity, we get great performance by putting them together in interesting ways and running them really fast. Now, how do you make switches? Well, you could use mechanical power. For example, in 1837, a large number of years ago, so this is the Charles Babbage designed. It wasn't built at that time. This picture that you see was a machine that was built later, beyond his lifetime, I believe by his son or grandson, I forget, I think his son. And then that was the first mechanical computer, the analytical engine. He did build the differential engine, which was more like a calculator. But that was not enough. So where computers came into their own is, of course, wars for all their negativity actually spur on technology. And World War II and 10 years maybe before that with Alan Turing and Konrad Zuse and so on, is where that same idea of analytic engine, except done with electronic switches, with vacuum tubes. And when I was growing up, the picture on the left, those are the vacuum tubes. We had a radio at home that had these vacuum tubes. So they're not that ancient, but using those vacuum tubes, and each one of those probably corresponding to 1 bit in this chassis. So these computers came to life at that time. 1951, ELIAC was built at my university, and if you go to the ground floor of our university, you will see I just took these pictures from the showcase there. So this was one of the first academic supercomputers, or academic computer, not leave aside supercomputer. Then in late 50s, the vacuum tubes were replaced by transistors. You can see a transistors-based picture. This is from probably early 60s, ELIAC 2, where you see transistors, circular things in the middle of the wiring. Then in 60s, you started getting integrated circuits. Many transistors were put onto a single chip. And that's where this journey begins. In 1971, Intel built its first microprocessor, 4004, which put an entire CPU on a single chip. In 1971, by the way, many of you are from Pune, so I should note I was just graduated from Modern High School and went to Ferguson College and started that journey as well at the same time. Then I went to BHU for my bachelor's, and 74, I started studying microprocessors. So I'm that old, yes. So 50 years is a fascinating story, and I don't mean my career. I mean what happened with these chips. You see this picture here. Well, this computer works on a clock. A simple computer, in one single clock cycle, it will fetch the instruction. It will do a whole variety of things, and all of them have to be finished before the cycle ends. The cycle has to be that long, and so these gate delays through the chips, through this matter a lot. So if you want to make it faster, you have to reduce the gate delays. How can you do that? If you make those transistors, which are all sitting on a chip, smaller, then they produce less. They have less, smaller capacitance, little charge to change from 0 to 1, so they can become faster. Also, if you can make them smaller, they can become cheaper. And so question is, can you make them smaller? And the technological progress is needed. The answer is, but it can be done, it turns out, as we know well. So this led to cheaper and faster processors every year. And in fact, this is Moore's law. I'm sure by now you have heard many statements of it. It's not performance doubles every 18 months, although performance doubling continuously is an interesting meme that we want to keep in mind. Actually, Moore himself didn't even say what's considered Moore's law. He said something very simple, which is, well, not simple, but something that he observed in 65 that looks like we are able to put double the number of transistors on a chip every year, and looks like it will continue for 10 years. It was an estimate, it was a heuristic, it was not a law. It cannot be a law of nature. So it's still going on in 2020. Look at this picture here. 1971, the 4004 had 2300 transistors, and you can see a straight line of growth. Well, a straight line is exponential growth because y-axis is logarithmic. Look at that, 2000 to 2.6 billion transistors. And I'll come back to why it's only that in this figure in a second. So, and that line is straight. I mean, it does sound like a law of nature, doesn't it? For the line to be that straight, how can just technological development be on a straight line like that? Well, I don't have time to take answers from you, but think about why that is. It's not a law of nature. Why did it sustain itself on that straight line? Not just growing in fits and bits, but just in that straight line. Well, my own answer, I don't know the real answer, but my own answer is capitalism and competition. So imagine a Fairchild engineer and an Intel engineer sitting in their offices saying, I just finished one chip. It seems to be performing well, right on the Moore's law and so on. And the boss comes and says, yes, but you know, the competition, they are going to be on Moore's law. Next year, they're going to double the number of transistors. We got to work hard to keep on that curve. So everyone put themselves on that treadmill for 50 years. And that's how we got this straight line curve. So it's like thinking that we can achieve it is how we achieved it, I think. But someone might have a better technical explanation than that, who knows? But now here, I said, if you make transistors smaller, you can actually make them faster. And sure enough, the frequencies, the clock cycle shrunk and the frequencies increased. I remember buying 33 megahertz computers in early days and so on. And then they kept increasing to 3 gigahertz. Hopefully someone noticed a trick in my picture here. The x-axis goes only to 2001, whereas the previous picture goes to 2011. Well, what happened in 2002, 3? Well, this happened. It actually stagnated around 3 gigahertz or 4 gigahertz, touched it maybe. And now you can see even in the last 15 years, it hasn't changed much at all, the frequency. And why is that? Well, that has to do with temperature, with the chips were getting too hot. And I won't go into the details of this, but it's a really interesting slide that Shekhar Burkar and his colleagues had made at Intel in 1999 that said, hey, chips are going to get as hot as the surface of the sun if we keep on this path. And of course we won't, because no one wants a laptop that hot in their lap. So then it stopped, the frequency scaling stopped. And you can see the power blue curve here stopped around 100 watts because we forced it to stop by not increasing the clock frequency, but the number of transistors per chip kept on increasing on this exponential curve. Again, y-axis is logarithmic. And then it has continued on. It's not 2011, 2020, and maybe 2021. We now have 59 billion transistors. In fact, M1 Max is probably a more general purpose example of that. So this curve has continued on. How long will that continue? Well, that's not going to continue for too long, although we have been saying this for a while, and that it has continued. But the current technology is maybe 5 to 7 nanometers, and silicon unit cell is half a nanometer in its size. So we are at the atomic scale now. We can't go too far without, it's like everything starting to fail. So I think we are at the point where maybe 100 billion transistors per chip is where we might end up stopping. And so by 2025, I expect Moore's law to stop. But now, even before that, when 2006 or 5, the frequency started not increasing, then how do you go faster computers? That's what we really wanted, right? Well, we have lots of transistors. What do you do with them? You can do architectural improvements like pipelining and so on. Eventually, we couldn't use that much. And then you had to use multiple processors on a chip to be able to do that. So you can put more processors, now called cores. And in fact, some of you older people might remember core was a completely different idea in early days. In fact, 2 different meanings it went through. This is the 3rd one. And so now we can put multiple cores, but remember, we want to solve one problem for the science problems, not your social media issues, but for these science problems, we need to solve one problem faster. We need parallel programming. And this is a good segue into, again, my personal story. Bill Wolfe is a very famous computer scientist. He came, visited IISc Bangalore in 78. I was a grad student at that time, and he talked about his parallel computing projects, C.MMP, Hydra operating system, and so on. And he said basically that, look, and he was the one who inspired me, one of the 2 talks that inspired me to go to higher studies in the US for and doing parallel computing eventually. But he said, look, the sequential processors are getting fast, but they cannot go on fast for too long. We're going to need parallel computing to make faster computers beyond that. Well, 78, actually, it turns out the engineers gave him a run for his money for his prediction, but eventually it came true, it had to. And so now we have multi-core nodes with parallel processing, we have accelerators, we have multi-node clusters, and we have supercomputers. So in this, so then that was my detour. I apologize for people who already knew all this stuff, but then I want to take the next step to talk about what these exascale supercomputers are and my own acquaintance with the exascale program in the US. So clusters are computers put together, connected by a network. You can put them in a cloud. That's just clusters in a cloud, of course. And then supercomputers are just bigger clusters with faster networks and a lot more money. In fact, early definitions of supercomputers was based on money. It said any computer more than $1 million is a supercomputer, but million doesn't go too far these days. So you need distributed memory parallel programming for these large computers, right? Okay, we'll come back to that. So let's look at the supercomputers that people have built over the years from 1990 to now. So remember now our point that we want single computers to be faster by putting, even if the chip frequency scaling has stopped and chip scaling will stop, looks like we can add more of them together in a supercomputer. Top 500 is a list that is published updated every 6 months. And what this shows at the bottom blue curve is the lowest computer on that list. That is minimum performance that's needed to get on this list. You can see around 2020, you get to, you need 1 petaflop to be in this club of top 500 computers, and actually more beyond that. And the orange triangles are the fastest supercomputer in the world that submits itself to these tests for top 500. And you can see that grows also, but not as smoothly, but in spurts. And that's because these are very expensive supercomputers. Once one becomes the top dog, then it reigns for several years before it's toppled by someone else, and then it reigns for several cycles, right? But in spite, under the green curve is sum of all top 500 computers' powers. Again, y-axis is gigaflops and teraflops, but it's logarithmic, and you can see mostly a linear curve, except for a little bend around 2010, 2013, and so on. So it looks like our some kind of an equivalent of Moore's slice going on here. We can keep making faster, larger supercomputers all the time. The top one right now is Fugaku. And the top one before this was Summit. It's now world's #2 computer, and that's the American supercomputer. I know something about the American program, partly because I've been in the US for this long and working parallel computing for 35 years. Supercomputing in the US, for those of you who don't know, is largely led by Department of Energy, which has the charge of nuclear weapons, and it has to keep the stockpile up to date and so on. But that's also the excuse to build supercomputers and use them for all kinds of purposes. So weather simulation and connected by energy and so on is actually led by the technology. The lead agency for the technology is Department of Energy. Around 2009, petaflops was achieved. I say around because there was a machine that was somewhat odd at that time that you may or may not want to count, that reigned at the top for a bit. And then exascale, which is 1,000-fold more, 10 to the power 18 operations per second, for double precision floating point operations per second, looked unsurmountable, looked like there are unsurmountable challenges there. And the energy consumption was predicted to be 100 megawatts to maybe even 500 megawatts by some measures in 2009 for exascale computer, and all these other three problems mentioned there were there. There's an excellent talk by Al Geist, who's one of the leading people in that field within DOE, and he gave that talk, and he basically said how this was overcome and what happened. What happened is we actually managed to build. Well, it is going to come online in the next few months, but it's clearly there, an exascale computer called Frontier for 29 megawatts, going from 2009 when we were here, 2.3 petaflops, we went 10-fold increase with only 6 megawatts to 9 megawatts, and another 8-fold increase only going from 9 megawatts to 13, and 200 to 1500, another 8-fold increase with only doubling of the megawatts. Now, 29 megawatts is not a piddling sum. You will pay $29 million per year in electric bill for that. So that's worth keeping in mind. But this computer will be built. Summit is the computer that already exists. I get a ringside view of exascale computing because I sit on a committee that reviews various software projects in that every year, and sometimes the hardware too. And so I got a good view of a Summit. Well, I think I don't want to go through maybe I have a little bit of time. Let's see. So anyways, it's 6 GPGPUs per node and 2 Power 9 IBM processors. So that was a daring step. I was not sure how using 6 GPUs is going to work, but DOE software people have made this work for many, many applications. It's still a challenge in my opinion. And all these challenges were then overcome by okay, let me come back to that a second. Let me just show you a picture. Here is me when we went to review this thing. We were called to Oak Ridge where this computer sits. So me standing in the middle of the Summit computer, the most powerful at that time, with other members of some of the other members of the review team and the DOE leaders within that project standing outside the machine room. So this Summit and then Frontier is achieved without exotic technology. It was an incremental step, not a giant leap. This is what Al Geist's talk said. And the reason for that is, you can say, what's the reason? Well, how come we managed to keep the power so low? Part of the reason you could say was accelerators. Memory bandwidth, high bandwidth memory was part of it, and several other technological improvement, but regular routine technology improvement. You cannot completely credit accelerators for it because the world's #1, Fugaku, doesn't have accelerators. It's a special purpose processor developed in Japan based on ARM. So you don't even, just routine technological improvement has given us this. Now, so will this curve that we saw of supercomputer performance, this one, Will this keep on going? That's kind of not quite Moore's law, but it's like, hey, we keep getting faster and faster computer every year. And so that will shift now, not so much to the desktop, but to supercomputers, and we'll keep getting faster supercomputers every year. Well, not really, because the limit this time comes from dollar cost. How much it costs to build the machine. It's not increasing linearly, but it's increasing at sublinearly, and at $1 billion or hundreds of $1 million. I think at some point a limit comes, and the operating power budget, as you saw, although data centers can run 100 plus megawatts data centers, but they have that kind of money. But anyways, okay, more on that maybe another time. So they will keep growing for a few years after Moore's law ends, but they will also stop growing beyond that. Now, I want to come to the topic of my interest, and I wish I had time to attend the previous talk completely, because the programming is my really main area of research. So I got to say a little bit about programming methodology for the supercomputers, as well as clusters, as well as cloud-based resources which need more elasticity. So all of these modern computers create challenges for effective parallel programming, also for productive parallel programming. If you look at the internet based things, we see quick evolution of programming methodology, whereas in HPC, mostly we are slowly migrating from Fortran to C++ and the same MPI plus OpenMP technology. But of course, it's still going strong. It works reasonably well as long as you have time to pay attention to it. One thing I should mention about the HPC program in connection with that is that in addition to the a couple $1 billion for buying those computers and funding the technology, there is about $1.7 or $1.8 billion spent on software technology. And when you say software technology, that doesn't mean buying software. That means funding people to develop software. So Department of Energy has these expert programmers in application domains, in computer science, and they manage to keep them not getting sucked into these Googles of the world by paying them reasonably and enticing them with this modern technology world. So some of this $1.8 billion goes to keep that workforce going. And it's a lesson for people trying to build, say, for example, in India, you may not have huge computers and maybe not necessary to build the largest supercomputer, but you need to invest on people who sciences, engineering, and computer science who can write parallel programs. So my own approach is something that's based on adaptive runtime systems and a parallel programming system called CHAM++. So the key idea in our parallel programming model is that we want to virtualize the notion of a processor. We don't want people to be thinking explicitly about processors and locality and so on. Locality only indirectly, but definitely not processors. And the programming system is called CHAM++. I'm going to give you a 2-minute introduction to it through some animation. So CHAM++ computation, when the program is running, consists of multiple collections of globally visible objects. For example, like this, there are 2 collections here, the blue collection and the whatever the other color is collection. And each collection is individually have objects that are individually indexed. So you can talk about green object number 7 or green, the beige object number 3, 4, 2. And then they talk to each other with async, and these are objects, literally C++ objects. So they talk to each other through C++ method invocations, but asynchronous method invocations. All right, that means you send a method invocation toward that object and not wait for a return value. If they want to send you something back, they will do another method invocation and then there are more advanced methods built on top of this, but that's the baseline. But reality, of course, is that there are processors. In fact, there are cores and nodes and whatnot, and the runtime system is in charge of assigning these objects to processors and, if necessary, changing this assignment. So programmer does not need to know where an object is located. So for example, and then on each processor, there are very many objects. So there is a scheduler, user space scheduler, that non-preemptively picks the next method invocation and runs it on the object that is the target of it. All right. Now, if the object on some object on processor 0, let's say the leftmost object, wants to invoke a method on object A sub 23, there it creates the method invocation, hands it over to the runtime, which serializes it, finds out where it thinks the object lives right now, and sends that packet of information and enqueues it in that processor's queue. That processor is executing other stuff. Eventually, it will come and pick this up and make sure that the object still lives here. If not, forward it to the right place, which happens very rarely. And if it is here, then run the method invocation, which may generate more messages that go to the other processors in the same fashion. This is the entirety of the CHAMP++ programming model. Of course, when you start learning, there are lots of details to learn, but this is the basics of it. But it turns out the runtime system now knows who is talking to whom, because after all, it delivered the messages, and knows who runs for how long, because after all, it scheduled them and non-preemptively. And so it knows which objects are heavy, which processes are overloaded, and then it can, from time to time, migrate these objects around to effect load balancing, for example, and to optimize communication. Hey, you object, you're talking a lot with that other object, you better sit on the same bench. Exactly opposite of what my teacher in grade school would do. But yes, we can do that. And let's see. And then, so then with this, actually, not only you get dynamic load balancing, you get fault tolerance, you get resource elasticity. You can change the number of nodes allocated to a job during execution by just redistributing the objects to differently, and variety of other optimizations, which is what my research group has been doing for more than 2 decades now. We built many programming systems on top of it. CHAMP++ is the foundational system, but on top of it, we built many more, including DSLs and embedded DSLs more recently, as well as the Python CHAMP for Pi here. This DSLs reminded me of the previous talk and so on. So there's interesting things happening there. Once you take this resource management to be out of the programmer's concern, we can optimize things a lot better. Now, this idea wasn't to just build a language and throw it over the fence. We co-developed it with many, many applications to make sure that our language actually caters to what people want. And so these are some of the applications we co-developed with CHAMP++, and NAMD is one of the most famous one. I'm going to show you an example of that. But this energy in co-developing these applications is what made CHAMP++ what it is today, which is very responsive to the real application needs. And there may be only a dozen or so supercomputer applications running on it, but they're running very well with it. So NAMD is a biomolecular simulation program, started with Klaus Schulten as a collaborator. And this is not something where we just gave them CHAMP++. We actually worked on my students worked on the design of NAMD itself, along with Klaus Schulten and Bob Skeel. And then more recently, some of you might have seen this picture, New York Times animation of the coronavirus inside a water bubble. So this is the simulation that they did on the Summit supercomputer with using several hundred, maybe 1,000 processors. This is the virus in the middle of the water bubble. Every atom of this virus and the surrounding filaments are explicitly modeled in some of the studies. So to be able to do those simulations is actually, now I'm not sure it's useful to the science. I'm not sure it's going to immediately lead to medicines and so on, but eventually it would. It's kind of fulfilling my original wish of wanting to use supercomputers for societal benefit through these kinds of applications. So beyond Moore's law, what happens? So individual computers like laptops and servers will stop getting faster soon, but the commoditization will mean they become cheaper. Data centers will keep growing, and I'm not going to talk too much about them. Supercomputers will grow for a bit longer, and I told you the limits why they would stop growing eventually too. There will be innovations in specialized hardware. And okay, one point I want to make. Let's look at the whole exponential growth processes. Moore's law was sustained by capitalism or competition. Like I said, it will grind to a halt by atomic limits. So it's like we're talking like big themes here. And the frequency increases stop because of thermal and energy issues. and supercomputers will stop because of, again, back to your capital and energy issues. So no exponential trends that are based on anything physical can go on forever, and we don't see any new general purpose technology in sight beyond that will take us beyond the current limits. But a lot can be done with what we have. We haven't scratched the surface of that yet. And so in summary, we need faster computers to make a positive societal impact with science and engineering. Well, I think I'll just put the slide here and stop. You can see it. Thank you.
Thank you so much. And I really appreciate this high energy so early in the morning. Very insightful, very, very entertaining as well. We do have time for some questions. There's one in the Q&A. I'm just going to read it out. It's remarkable that a general approach, adaptive runtime, is versatile enough to keep up with 35 years of changes. Is there a snapshot view of some of the changes that had to be made to keep it going? The charm C++ analog of the historical microprocessor architecture walkthrough. So how did the charm++ had to be evolved over the years?
Yes, that's a very good question. In fact, NAMD is a good example of that. Although I must say, even though my research goes 30 plus years, charm++ as it stands today is probably more like 2001 or 2. We had a system called charm++ before that, but it wasn't the same. So you know what they say about programming, what will be the programming language of the future among the community that I hang out with. They say, well, I don't know what it would look like, but it will be called Fortran. And so it's like that, charm++, but just it changed quite a bit in the early years. But essentially, if you look at the NAMD example, the idea that you can decompose computation into the separation of concerns, where you put computation in terms of objects, and then you design the algorithms keeping isoefficiency and scalability considerations in mind. Some of you might want to read about what isoefficiency, Vipin Kumar's concepts are. It was designed with that in mind. Therefore, it had scalability built into it, the algorithms. It's not enough that the language be like that. The algorithm has to be scalable also. So it kept going through these generations, pretty much making things fine-grained if needed. So instead of an object representing a 14 angstrom by 14 angstrom by 14 angstrom cube, maybe it's 7 by 7 by 14 angstrom cube, so making them tiny for the blue gene-like processors, but the basic methodology remained the same. This indirection, you know, Alan Perlis had lots of sayings that are famous now. One of them is there is no problem in computer science that cannot be solved by one more level of indirection. And here, by separating the concerns by moving, expressing computation in terms of objects and letting the runtime system put those objects on processors, that indirection helped us a lot to tide over the multi-core. When we went to the multi-core revolution in 2006 and 10 onwards, we had to modify the runtime system, but not the application programs. Now, when the GPU revolution came, that actually was different, but someone had to write the GPU kernels. We are not doing compilers, but those kernels and asynchronous handling of those kernels can easily be done by the same basic methodology. And really the tenacity of my students is what kept us going, I would say, because anytime people use this, they basically are sold to the idea and then they keep working on it. It was easy enough to give up maybe 15 years ago or 10 years ago, saying, okay, people are going with MPI, forget this. But and the tenacity of the dozen or so applications that use us. I don't think there is any magic in the programming model. The programming, there is, but the programming model is what it is, and we keep changing the runtime system to match the newer hardware. Astrophysics is what I dropped my 2 slides that I had because I didn't have time when I checked last night. But astrophysics is very interesting. it's the other end. I mean, we work on quantum chemistry, one level below. Biophysics is angstroms and femtoseconds. Quantum chemistry is slightly lower than that with electron clouds and so on. And at the other end, we go the rocket simulation, and then we go to the space with megaparsecs and cosmology, which is my collaboration with Tom Quinn at University of Washington. And there's a program called CHANGA, CHANGA, charm-based something gravity solver. So don't ask me to expand the acronym, and then more recently we developed a system called ParaTreat, a framework called ParaTreat, that's parallel tree toolkit on top of Charm++, that allows you to build that kind of gravity type of application, cosmology type of application. A simple one, for example, was done using just 130 lines of code. It's kind of a DSL-like approach there, but mostly just library and compiler based. That's what we have done in the astrophysics applications. Those are also very challenging, and we're going to become very current as we get this new data from telescopes and start mapping the universe at much finer granularity than ever before. Dealing with that much data all at once and doing all kinds of operations on that is going to keep us busy. I don't think I can say that much more unless you have a specific question, but I will be happy to talk to you afterwards.
Thank you. There's another comment, but maybe one question from my side. The examples you gave are very much in the area of research and simulation. Are you aware of applications of Charm++ or something built on top of that are outside of research and science?
Yeah, this is the problem. So we have been trying, and I think my introduction says I'm a CEO of a company. What that is just a spin-off of our research group and trying to sustain the software. You cannot sustain the software with grants because they go up and down, and they always want earth-shaking research, not software maintenance. So we did that company. The idea was, hey, we have been very successful with biophysics, and that's a great example. Astrophysics, variety of, and there's other astrophysics projects that have used it and so on. But if you think about astronomy researchers don't have money to pay us, nor is their funding model in NSF such that you could say, hey, I'm using that software. Can I use some of my grant money to maintain this software? You cannot do that. So we thought we will go to engineering, which is where money is, and then get the engineering companies to pay for it. And we're still at it. And there are some engineering applications that work. We are doing data analytics now with Python. So if you talk just from applications point of view, I think Charm4Pi and the data analysis applications and also some machine learning offshoots from there are going to be there for that. These distributed objects can even live in distributed systems, right? But we haven't explored it that much. You can do parallel computing on a dedicated cluster, but what about, put one of these actors, one of these objects on some remote machine 10 miles away or 100 miles away, and 10 objects here, and they are together computing some function? Can be done. So we haven't explored that part of it. We have explored simulations, discrete event simulations with it. And the engineering side of it, though, the problem is these engineering codes that ANSYS and other companies sell, they are very entrenched. They have their customer base. And to do something greenfield, completely new, is not in anyone's immediate interest. And so this is the problem. So it's a chicken and egg problem. We talk to them and say, yes, yes. And some of them even go further and say, yes, but we have the next release to worry about. And so their energy is all focused on next release and keeping their existing customers happy. I think the only way this is going to catch is someone coming from the left field with a new company, creating a new product and saying, then forcing everyone to pay attention. But that's a failure, I would say, in response to your question, that beyond science, we don't have as much results, and for the reasons I mentioned.